Greetings, everyone. Welcome back to our lecture series on Morse theory. And according to the last lecture, I realized I made a lot of mistakes in making the video just because it was like really late and also yeah, there was many accidents that happened that day, but I won't give myself any excuses. I am sorry for all the typos I made in the last lecture. I have addressed, I think, most of those in the comment section. And if you find more, feel free to comment there and roast me if you want. I do not care. As long as you guys are benefiting from these videos, I would be more than happy to take any criticisms. And there's also a major overlook on my part that I was sharing my screen, but I forgot to share the plot of the saddles. Um, today, so in the beginning of the lecture, I am going to show you the monkey saddle as promised. So let's look at this picture. Hope you guys can see this right now. I'm going to double check. So I think I am sharing this monkey saddle right now. And as you can see here, this red dot is the monkey saddle in the middle. And um, let's rotate this a little bit. And you can see from the contour, this looks really interesting, right? This is a saddle point. And it's also actually a degenerate saddle point. So if you look at this contour, kind of looks like x to the third from this angle, right? So it's like a cubic polynomial. It's kind of like inflection point here. And then, yeah, here you get this little inflection point, and here you get this. And you can see the surface looks very interesting. There's like a very flat area in the middle. And yeah, basically, I want to show you this example to show like degenerate saddle points are usually much harder to deal with, and they're really difficult for us to give them characteristics. So that's why we want to focus on the study of non-degenerative saddle points. But not that we're saying that the degenerate ones are not important. Of course, they are. They're just much harder for us to analyze. But yeah, people also study those. And then in chaos theory, a lot of people study these with like bifurcation and catastrophe theory. And there's a bunch of these. If you're interested, feel free to search those keywords. And I'm sure you'll enjoy these if you really enjoy looking at weird behaviors of complex nonlinear systems. And yeah. Anyways, let's not deviate too much from today's content. And yeah, I just want to show you guys this because I have promised to show you guys the monkey saddle, and it is a very interesting case of a degenerate saddle point. And let's close this real quick. And I believe we are not sharing anymore. Okay. Bear with me. I am going to switch the screen. Here we go. So let's see. Share. Okay, share screen, start broadcast, and hopefully you guys can see. Yes, I think you guys can. Okay, great. Let's do a quick recap on what we've covered last time. So the first thing we covered is the coordinate transform. Why do we need this? Because we want to use this very important linear algebra proof slash fact to prove this very important lemma, which is actually, ironically, an actual theorem called Morse lemma later. So basically, what does this coordinate transform do? Basically, it's saying that no matter how we express our coordinate, so here we can express our uh, non-degenerative saddle points. I'm going to do abbreviation here in basically a different coordinate system, in different coordinate system. And This will not affect the property, which if this point is a degenerative saddle point slash non-degenerative saddle point, the property persists no matter how you change your coordinates, which makes sense, right? Because like you should preserve your property. You're just changing a local coordinate. You're changing how it's expressed, right? But then this shouldn't actually affect anything. And let's erase this. And the proof is kind of tedious, so we kind of just took it for granted. And basically, we just say, oh, yeah, this is important. We're going to use this to prove the Morse lemma. And to prove it, you need the product rule and the chain rule. Basically, if you know about calculus and just go through the tedious proof and yeah, but we're not going to do that. We're going to take it for granted. And here, we use this to prove this Morse lemma. Morse lemma is super important, right? And it's kind of long, so I'm gonna give you like a Spark Notes version to show you what it is. Okay, so basically we have a point, P naught, and it's non-degenerative, non-degenerate, degenerate. I also realize that I say degenerative and degenerate kind of interchange oh gosh, I can't talk interchangeably. So like they are the same thing. And sometimes I say non-degenerative because that's like an adjective, and non-degenerate seems to be like a non to me. But just so you know, the right way to actually say this is non-degenerate. But yeah, non-degenerative is just a little bit more natural to me. But yeah, the correct terminology should be non-degenerate. Just so you know, but yeah, that's just a habit. I don't think it's a big deal. If you feel to be annoyed, let me know. I will try to make sure I don't say that word next time. I'll be like, bad James, shouldn't say that word. Okay. Um, okay, great. So we have P naught as non-degenerate critical point, and it's a function f. So we have a function f, right? And then we can choose a an appropriate local coordinates x, y, big actually small x and small y. I made that mistake in the last lecture, and that carried over. Small x and small y. So this is what we're given. So we can choose this in such a way that the function expressed with respect to the big X and big Y takes one of the following. Oops. Takes one of the following standard form. So we have three standard forms. The first one, f equals to big X squared plus big Y squared plus C. And second one is x equals to big X squared minus big Y squared plus C. And the third one, not surprising probably, is, oh, big X, sorry. F equals to negative big X squared minus big Y squared plus C. So right, those are very simple quadratic forms, and in our proof that we showed in last lecture, we know that we also have another one that's kind of like negative x squared plus y squared, right? Plus c is kind of like that offset. But yeah, basically those two are the same things, right? They follow the same form. They're if you just flip the axis of big X and big Y, right? So I'm just gonna ignore this part, which not a big deal, right? And okay, um, and yeah, C is some constant. I'm not gonna write these down. Those are kind of not that important, and P naught is the origin 0, 0. Okay, so those are the key ingredients of what Morse lemma is. Basically, what this really tells us is that functions look really simple. I'm going to reiterate this because this is very important and this is the key takeaway. So functions look really simple. Look, I underlined this and then I added a red box to show you why this is so beautiful and so elegant and why this needs to be re-emphasized again and again because it doesn't get much better than this, right? Like a function can be so complicated, but you can reduce it to such an easy quadratic form near a critical point, and namely a non-degenerate. Oh, I can't spell. Degenerate. Yeah, here we go. Degenerate. Yep, that's not right. Hold on. Non-degenerate critical point. And yeah, we can use some coordinate change to make it super simple. And another corollary that we got from this theorem is that all the non-degenerate critical points are isolated. So yeah, I'm not gonna write this down, but it also holds for n variables. We're gonna talk about that later. Okay, this is a very long recap, I know, but last lecture was super important, and if you haven't seen it, I suggest you to watch it before watching this lecture. And also, this was a long lecture. So I do apologize. I do want to make those short and sweet, but sometimes I just keep yapping. I know, but I'm trying to make this as concise and as short as possible that you guys can actually get all the content you need from these lectures and still have fun with it, right? But at the same time, this is my first time doing it, so I do apologize for some rustiness in my online teaching style. I do teach, I think, much better in person, but at the same time, like this is a new, uncharted territory for me, and I do appreciate your patience. And I will get better over time and try to make this more concise and more interesting to you guys. Okay. Anyways, enough for the recap and the yapping about the previous stuff, and let's move on to today's content. And I accidentally clicked on something. Give me 1 second. Sorry about that. Um, okay, so today, what are we gonna do? So, as the title suggested, we are going to cover first. Well, the first thing we're gonna cover is the Morse function. But before we talk about that, we need to talk about indexes. And the second thing we're gonna talk about is what a Morse function is. And I do realize that maybe these two content will take quite a bit time. So let's see. Maybe we will cover diffeomorphism, which is my favorite thing to talk about. So I'm going to, yeah, I forgot to write this Morse function. Diffeomorphisms, maybe. Okay, let's see. Well, we will try to keep this within let's say 30 minutes. How about that? I think most people's attention span nowadays is probably like 15, well, probably 10, honestly. 30 is a lot for most people. And even if I try to make it as entertaining as possible, this is kind of difficult for everyone to, like follow. And also, it's like math content, right? It's kind of it's easy to get boring and tedious. So, well, my goal is to try to get you interested in the subject and make you, appreciate this more and give you enough information so that there's enough knowledge to be imparted and at the same time, you gain more interest in this subject. So like, yeah, I'm not trying to overwhelm you again, but if I am doing such thing, yeah, also do let me know because there's a comment section and that's what it's designed for. Anyways, okay, let's move on to today's content. So first, let's give a definition. That's kind of like a continuation from last lecture. So recall we just look at those three forms, right? So let's see. I'm going to try something here real quick. Can I copy paste this? I didn't copy the. Ooh, that's nice. Let's see. Can I copy? Yeah, copy. Yes. This is my first time using this. Oh, this is so cool. I'm like so impressed with this, by the way. It's actually not that complicated, but yeah, I'm just very easily impressed with technology. Anyways, here, those are the forms that we just saw, right? The standard forms of our Morse lemma, right? So here we're gonna give a definition. So this is the definition for index. So let's state the theorem. Let P naught be a non-degenerate, degenerate, oh, I misspelled again. Spelling is a hard thing. And as someone who learned English at the age of 14, I think I do pretty well. Um, but yeah, I don't want to toot my own horn, but I think I do a pretty good job. Although my handwriting is atrocious, I know, but at the same time, it's kind of difficult to write on this mini iPad with Apple Pencil. So, well, okay. So yeah, let P naught be a non-degenerate critical point of a function f of two variables. We choose x and y in some neighborhood of the point P naught such that f has standard form. And we're going to copy this down. So I just realized I should have done this, yeah, right now rather than earlier. But we missed those twos. So let's see. Let's get those twos back over here. Yeah, perfect. Nice. So we got these, right? And we missed the dot, but it's fine. I'm going to add that right here. So for the first case, we have index 0. The second case, we have index 1. And the third case, as you can guess probably, we have indexed 2. There's one way you can tell from the index, right? Um, if you just count the number of the negative signs slash minus signs, this should equal to the number of index, right? This is a pretty easy observation that you can make, correct? So yeah, and in other words, oh, other, yeah. So in other words, there exists. By the way, this little sign, I don't know if I introduced in the last lecture, but this little sign basically means exists. So in other words, there exists a J, a Jacobian, such that in our previously mentioned coordinate transform lemma and our fancy H, we have this. This is a diagonal matrix. So what does this have to do with the previous, right? So this is basically what we are trying to do. So to get all of our critical points in this standard form, we can use this. Yeah, so here we want to express all of our standard, uh, critical points, right? In this form, the big X and big Y, right? Right here. But then we choose small x and small y in some neighborhood. So we need to use some coordinate transform, which involves the Jacobian to do such thing. And then we can basically massage slash, transform our points to be expressed in such a way that this Hessian of our critical point is actually a diagonal matrix. So basically, it's easier for us to view the properties of our points by doing this coordinate transform. Okay, great. So now we've covered this definition, we can actually start by talking about Morse functions. So let's give it a heading. So I realized for the last lecture, I typed everything on LaTeX, but I haven't given them the proper heading. So right now it's actually supposed to be section 1.4, but I will make sure to memorize this next time. Anyways, we can talk about Morse functions on surfaces. So first, let's denote some conventions for us. So we denote spheres by S2 and a torus by T2. What does a sphere look like, right? So this, I'm terrible at drawing, but I'm still going to try that. Sphere kind of looks like this, right? So we have this, not too shabby. Okay, well, what about the torus? Oh, this is going to be hard. Kind of like a donut, right? So we have da 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 da. Da, 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 da. Okay, not too shabby. Also, if you want to take a look at a better picture of a torus, make sure to look at the cover of the this playlist, the Morse theory with no background, basically playlist cover. There is a picture with a standing up torus. That's a perfect example, and it's a much better picture for you to view. And anyways, we also have another convention here. So this sigma g subscript g is the closed surface. We will define what closeness later. Of the genus, I believe it's pronounced as genus, but double check. So what is genus? Genus is the number of holes of a closed surface. So as we can see, if we do this, this sigma zero, zero means we have zero holes, right? So what object has zero holes? A sphere, right? And if we do this, this means we have one hole of this closed surface, right? So this one hole, you can see a torus has one hole, right? So we know this is a torus. And a closed surface also in this way, intuitively, it's kind of like a finite surface that encloses itself, right? So this surface is kind of like constrained in some domain, right? So this is not like going into infinity. This everything also like kind of connects to each other, right? So I don't know if you're familiar with the Morbius strip, and that's also enclosed one. But anyways, let's move on. So let's this space M be a surface, and we call a map F that maps from M to real numbers, which assigns a real number to each point P of M, a function on M. Oh, on, I already wrote on here. Okay. So, and I realize this is blocking, so my apologies. I should have put this on the top earlier. Okay. So, we define a function, and if a surface is curved, that's kind of tricky for us, right? So usually people are more familiar with a flat surface, but look at those like toruses and spheres, right? So this things get start to get very interesting. You're working on a surface where you don't have that very nice property of like, oh, everything's flat. You can just pick a point and you can pick whichever point, right? But if a surface is curved, you're constraining a certain set, right? Like things actually start to get very interesting. If you know what I mean, like this is very exciting. Like you may think, oh my gosh, like curved surfaces, this seems to be like kind of hard. But yeah, life is hard. Get over it, right? But also like the Earth itself, right? It's curved. And just a quick rant. Basically, like if you think about how we like make coordinate systems on Earth, we actually make those Cartesian coordinates, right? Like three-dimensional Cartesian coordinates, like X, Y, Z. This is kind of taken for granted for most people. But this is only because the Earth radius is so large. And we're pretty much like little ants on a huge surface, right? So if you look at a particular point, this point kind of looks like on a flat surface. So you can kind of do approximation like that. So every little point on the surface is kind of locally Euclidean. This is an interesting concept, right? So this is also like how you define what a manifold is. But anyways, let's not get too deep into that. But you know, the intrinsic of what the Earth is, we all know the Earth is basically we need to get on the same page on that first. The Earth is not flat, okay? This is actually a sphere that we're working on. The sphere just has a really, really large radius, right? So like we are actually working on a curved surface. Things start to get super interesting. We can actually like do a lot of interesting physics problems on this, by the way. Anyways, a quick rant. And if we have a surface that's curved, so that means our local coordinates on it are also curved. Weird, huh? And we say a function f that maps from M to R defined on a surface M is of class C infinity. Ooh, let's make this red. C infinity with respect to any smooth local coordinates at each point of M. What does smooth mean, right? So let's give a quick intuitive sense. So let's look at a sphere, right? Sphere looks like this. So every point. So smoothness also is kind of about taking derivatives. So you can take a derivative here, right? So first order derivative, first order derivative, first order derivative, first order derivative, right? So you can take it infinitely many times, and this is still smooth. But let's also look at a corner looking thing. So if you have something that's like this, like an absolute value function, right? So can you take the derivative here? You can't, right? So that's not desirable. That's basically non-smooth. And intuitively, if you just look at this, like a little sharp corner, a cusp, that is not smooth, just intuitively speaking, right? So let me erase all this and oops. And these are actually terrible drawings, but you get the gist, right? Okay, great. What does this mean for us? So let's look at critical points. So the concept carries over for our weird surfaces, right? So a point P naught of a surface M is a critical point of F that maps from M to the real numbers if if we have the following. Oh, I clicked on something again. If we have the following, so the partial derivative of our f with respect to x at point p naught equals to 0, and the same thing with okay, that wasn't what I was trying to do, but the partial derivative with respect to y of p naught is also 0 with respect to the local coordinates. So does this make sense in some neighborhood of p naught? So if you have like a curved surface, right? So like you can have different local coordinates to express your points because yeah, as I said, like we can have like a really big sphere, right? So every local point you will have your local coordinate systems to express points because your surface is curved. So it's a little bit trickier to express these points. But yeah, basically they're all those critical points are pretty much like local. You need the local coordinates to express these. Anyways, so also we are able to do these um, partial derivatives because we have a smooth surface. So like our cusp, our little corner example, right? So we can take a derivative on these points, and because we don't have this C infinity um, property, and we don't like that, right? So because we don't like that, we don't want that in our definition for critical point. And also, yeah, this just comes up naturally. Okay. Anyways, now we need to define what a Morse function is, and I think we can call it a day. I just realized we don't have time to talk about diffeomorphism. Maybe we'll talk about a very quick example to give you some intuition. But then, like, yeah, and there is also an upcoming theorem which I will spend quite a bit time to talk about because it is correlated to diffeomorphism. And I don't want to start this big topic before, like um, introducing the definition. And this will take a while. So yeah, just bear with me. We should be fine. Okay, so let's quickly define this. Ooh, it should go back to black. Oops. Okay, so definition, Morse functions. You had a little star here because those are very important. They're a special class of functions. So suppose that every critical point of a function f that maps from a surface to R on M is non-degenerate. Then we can say that f is a Morse function. Oops, Morse. Okay, that's it. That's it. As simple as that. If every critical point of a function on of f is non-degenerate, then we can say that f is a Morse function. Okay, great. What can we do here to give you guys some visualization? Let's see. So let's look at the sphere. Okay. I just realized I probably should draw the coordinate system first. So let's do that. So X, Y, Z, right? Standard. X, Y, and Z. And we have, let's kind of draw a circle here just for reference. This is like a unit circle on XY plane. And we're going to draw this. Oh, this is ugly. Ooh, let's redraw this maybe. Okay, not much better, but well, we'll work with this. Okay, so this is kind of use your 3D vision here. This is actually three-dimensional. I know it's kind of hard to convince, but this is three-dimensional. Okay, let me make those a little bit longer. Yeah. Okay, great. So we have a sphere here. And let's look at a point P over here. It's on the surface. So it has some height here. And this function is mapped to a real number, z. And if we look at this point here, that's 1. If we look at this point here, that's -1. So that's a quick example of what a Morse function may look like. And yeah, these two, the top one will be the critical point on the top, the bottom one will be the critical point on the bottom. So that's sort of like the North Pole and South Pole, right? So yeah, so what this example is yeah, S2, which is our sphere, defined by x squared plus y squared plus z squared plus 1. So we're describing a surface, right? So any point on this that satisfies this particular equality, which is on the surface, is S2. And then, yeah, we let f that maps from this surface to R, which is a function on the sphere, and it assigns to each point P of x, y, z on S2 its third coordinate. So we're just basically giving it the height. Does that make sense? It should. So yeah, we have our P naught and Q naught, the North Pole and South Pole. Let's denote these. P naught, Q naught. Yeah, these two are the points, right? Great. Okay, and our function does the following. So function maps from x, y to z. And z equals to 1 minus x squared plus y squared. Okay, so that will represent our height, right? And then we know this is a classic double cover problem. Basically, we have 2 points at a particular x and y coordinate, right? So as you can see, we have northern hemisphere and southern hemisphere. And if we look at a particular point like this P, it has a counterpart that's on the bottom that corresponds to the same x and y value, but it's negative in z, and they have the same magnitude. That makes sense? So this is going to be covered later too. Spheres are very interesting objects to work with. And yeah, and before we talk about this more, because this will actually get much deeper, and this will get to diffeomorphism very soon, which is, yeah, the upcoming content will literally be a theorem on diffeomorphism, and we will bring a lot of things together. So let's actually stop here. So next lecture, we are going to actually cover diffeomorphism. Morphism. Yeah. So, yeah, thank you for listening to this lecture. Again, I am very thrilled that many people gave me likes on my previous videos. Thank you so much for the support. And if you feel like this is helping you to gain more interest slash helping you understand some of the content, I am very glad that my effort actually, provided some useful content for you. And feel free to like and subscribe to my channel if you feel so inclined. And I really appreciate all the support and all the help from all of you guys. And yeah, also feel free to give me constructive criticisms and feedback. I will try to improve my lectures. And yeah, I will see you next time.